Okay, good afternoon, and thanks. I'm Robert Hormuth from AMD, and I have to say this will probably be the speediest talk I've ever given. So I've got 5 minutes, so I'm going to do like 4.5 minutes of talk and 30 seconds of Q&A. So we'll see how it goes. So what I wanted to talk about today was just changing the topic a little bit from we're apparently this has become the OCP AI conference. But CPUs do matter. We do care about CPUs still. But there's an important thing going on in the CPU landscape. If you kind of look at the era where we're at, we're really in this era of core scaling. And we have been for a while. And what I have plotted up there is just, you know, the kind of the core growth between AMD, Ampere, and Intel over the last number of years. And it's kind of a mix of announcements and a mix of shipping, because sometimes people announce and we don't know when they're shipping. So I just put up there kind of the best case announcement dates, and you know, for AMD it's mostly shipping dates. But you know, there's a progression that the industry is on core scaling still, and there's a good reason. From an overall energy efficiency reason, it's kind of like, well, why do we keep scaling cores? Well, it's the easiest tool that we have in the toolbox. It delivers the highest performance. It delivers great efficiency still. It's very scalable. Almost everybody can get more work done with more cores. And you know, it helps drive down cost. You know, the more that we can package in an SoC, the more we can drive down platform cost, SoC cost, better die yields with little chiplets and so forth. And it's been really enabled us to kind of break the chains of Moore's law and get past the reticle limit of silicon in a package by moving to chiplets. And so it's really helped us drive all of those metrics in terms of scalability, cost, and sustainability. And the resultant has been really good, as Forrest talked about in his keynote, you know, with the energy efficiency. We're on a pretty good trajectory of improving energy efficiency still by core scaling. And this is just a chart on the top right of kind of the best published scores in spec power in terms of their overall performance at 1P, 2P, AMD, Ampere, and Intel. And this is just simply the best published. We can't do anything better than reveal what's out there that's published and verifiable. But a couple things that are interesting here, if you look at a couple observations. You know, for the first time in probably our history, 1P and 2P, at least for AMD, the performance per watt efficiency is about near equal. The two bars if you look at the purple line at the very top left, you know, the performance per watt for our 1P and 2P are dang near identical. It used to be 2P always won the spec power war because you could drive more into the server. But with the efficiency and performance that we've been able to drive with core scaling, we've been able to improve that to where it's almost equal. It's just a slightly different. And you can see the range of the competitors in terms of the overall SSJ ops, and then the performance per watt is that purple bar. But you know, continuing the path of core scaling, though, there are still some problems that we in the industry need to address. You know, there are some challenges. There's a fair amount of fear in customers on high core count adoption. There's fear of isolation, or too many eggs in one basket, or noisy neighbors, whether it be cores or accelerators for that matter. Anytime you integrate an accelerator in an SoC that was optimized for CPUs, accelerators can throw it out of balance really quick because they're big memory bandwidth hogs. And then you've got the OS application scheduling, you know, impacts that can really impact how do you take advantage of this core scaling. And what we did here was we did a test to try and mimic, you know, some noisy neighbor, or what happens with core scaling when you really stress out an SoC. And what we did here was we plotted. We basically ran stream triad on core 0, and that's what the red bar is for the AMD system there for the Bergamo. So we measured and tracked, you know, the core 0's memory bandwidth, the stream triad, and then we launched, you know, additional copies of it, starting at core 127, 126, 125, all the way down to core 0. And we plotted the impact of that memory bandwidth per core. And you can see on the Bergamo system, it starts to fall off and has a linear decay, and then it kind of falls off at the cliff at the end. And that's the artifact of introducing a lot of noisy neighbors. Now, we have a a distinct architecture advantage compared to other folks today, because we basically have a centralized pool of memory bandwidth. If you look at the way we architect our chiplets with discrete chiplets of core cache complexes and then a centralized I/O die, so we have a central pool of memory. Everybody else is doing a distributed pool of memory. And so you run into a lot more noisy neighbor problems when you have to cross boundaries. It can be a little bit more lower latency maybe, but you end up, the artifact is this distributed memory bandwidth. And so we did the same thing on the latest and greatest Sapphire and Ampere. And you can see we start higher. Yes, we have more channels of bandwidth, so you expect that. But if you look at, you can really see the impact of this distributed architecture of memory bandwidth versus a centralized pool on both the competing ones. But what's really important to me is about, well, what do we do about this in the future? And so we've got some really cool features in the EPYC family today around quality of service. And so we can actually create multiple classes of service. We can assign cores and threads to classes. We can tell those classes how much L3, how much memory bandwidth. And so we can actually start to ring fence in cores to protect themselves from multi-tenants or other tenants or higher priority applications. And so this is in the silicon today. And so we ran the same test, and the top bar on that one where it doesn't flatten out as much as Bergamo with quality of service turned on. And so for all the other noisy neighbors, we put in a 50% bandwidth cap. And so you can see it did degrade still a little, but not nearly as much as that first one. And the point of this talk is really not so much about, this is really about highlighting, the benefits of multi-core, the challenges of going to multi-core. But, if we want to take advantage of this, and we want to take advantage of classes of service and quality of service, and how do we as an industry make this easy for the applications, for the schedulers, for the OSs, to really start to take advantage of these kind of capabilities of classes of service and quality of service, so that, we can effectively keep continuing down this path of core scaling, so that the end user and the customer gets the benefit of being able to get that performance with the determinism that is required to meet your end user and SLAs. So that was my call to action here, that I'd love to see participation from OCP on how do we go help define this in a more industry standard way. We don't need everybody doing it different. We don't need everybody doing different APIs. We don't need different things in ACPI or special libraries. We need to enable this for the broad industry, so that application developers, OS, libraries can take advantage and to be able to take advantage of this capabilities in the industry, so that we can drive better utilization and efficiency. So my call to action is, if you're interested, reach out to myself at AMD or any other AMDer, and let's see if we can get a solution that the whole industry can adopt in a common way, so we can all take advantage of this in the future. So I think I'm done and out of time, but if they'll let me take any questions, I will.
Any questions? No. Thank you so much, and I would like to welcome our last